Hello, in this video we will talk about the ideal gas law, calculations with the ideal gas law, and how that relates to laws named after various scientists, Boyle's, Charles, Avogadro's law. Okay, so I start here. I start with the ideal gas law. So the ideal gas law, in the middle red box here, it relates pressure, volume, the number of moles, and temperature for a given sample of gas. So if you have some physical sample, say enclosed in a balloon or something like that, or some other container, the pressure times the volume of that sample of gas is equal to the number of moles of gas times some constant times the temperature. And this constant is called the ideal gas constant. And in units of liters atmospheres per mole Kelvin, it has a value of 0.0821, say. And we call this R. It's kind of weird, but we wind up using the ideal gas constant in all kinds of different places in chemistry. It comes up a lot. Anyway, so that's the equation of state for an ideal gas. Now, from this equation of state, you can take a look at it and say, all right, well, if you change the volume and you look at what the pressure would be, okay, well, pressure times volume equals something unchanging, assuming you have a constant number of moles and constant temperature. Well, if you increase the pressure, you got to decrease the volume to have them be equal to the same thing. And so that's what this says. If you increase the pressure, you decrease the volume, so on and so forth. And so we'll talk about that in an upcoming slide. We'll talk about how the volume and the temperature are proportional to each other, because since they're on opposite sides of this equal sign, if everything else doesn't change, if you double the volume, you're going to double the temperature. Therefore, they're proportional to each other. A brief aside that's useful for learning science, this little symbol right here means proportional to, and you can rewrite that as saying that's equal to whatever times a constant. And so this is saying volume is equal to some constant times temperature, and that's another way of saying it's proportional to. This means what I said a minute ago, that if you double the volume, you double the temperature, etc. For the one above here, we would say this is inversely proportional to. If you double the volume, you half the pressure. So this is proportional to 1 over the other thing. Okay, the volume of gas is also proportional to the number of moles of gas for the same kind of reason. Let's look at each one of these individually because they're illustrative of how gases behave. Okay, so first, our assumptions for what makes an ideal gas. In an ideal gas, the molecules do not attract or repel one another, and the volume of each molecule of gas is negligible. Gas molecules are small, they're pretty far distance apart, so that actually works out. And then many gas molecules are not interacting with other gas molecules to a large degree, so that actually works out pretty well too. When you're in a normal pressure, temperature range, the ideal gas law actually works out pretty well. There are exceptions to it that we'll get to in a later video, but overall it does a good job and it's pretty simple of predicting how a gas behaves. Okay, so Boyle's law. And so this came before the ideal gas law, but I talk about it in context of the ideal gas law. And it says that pressure is inversely proportional to volume. So if you have a balloon that has some volume of gas in it, and then you put it in the squeeze and increase the pressure on the balloon, then your volume is going to decrease. Now, we can't actually do this in reality because usually you just pop the balloon instead. But if you had some much stronger container over here with a sample of gas in it, and you put that sample of gas under high pressure, you'll have a low volume. If you put that sample of gas under low pressure, you'll have a higher volume. Now, when we're talking about Boyle's law, we're considering that the temperature is constant and the number of moles of gas are constant. Otherwise, this doesn't make as much sense. And you can write this kind of equation that the pressure times the volume in one state is equal to the pressure times the volume in the other state before and after a change. So what is the molecular basis for Boyle's law? Well, gases consist of small molecules pretty far apart. And so if you have those small molecules in a larger container, they hit the wall less often. But then if you make the container smaller, so you reduce the volume, the same gas molecule is going to collide with the walls more often. And remember, gas molecules colliding with the walls lead to pressure, so this will lead to an increased pressure. So there's less collisions and lower pressure on the left for a larger volume. There's more collisions and a higher pressure on the right for a smaller volume. Okay, that makes sense. Now let's talk about Charles's law. This is the relationship between volume and temperature. So as you increase the temperature, you increase the volume. If you decrease the temperature, you decrease the volume of a gas. So the little picture here is trying to show that if you have some volume of a gas and then you heat the thing, you'll have a bigger volume of a gas because you heated up the sample and increased the temperature. And this is assuming that the pressure on the gas and the number of moles of the gas is constant. And so the plot on the left is showing the same thing, that if you have a small temperature, you'll have a lower volume. If you have a large temperature, you'll have a higher volume, things like that. You've probably encountered this in your life before, either pressure inside a Tupperware container that you put in your fridge, or pressure inside tires when you drive and then it heats up the air inside the tire, things like that. It's a pretty commonly encountered property of gases. Now the molecular reason for this is that as the temperature increases, the speed of the gas molecules increase, and so the gas molecules will collide more frequently with the walls of the container. Now, if pressure is held constant, that means your volume's going to expand, which hopefully makes sense just on its face. Now, an interesting outcome of Charles's law is as you keep decreasing the temperature, if you extrapolate this all the way as low as you can go, you'll find some minimum point where your volume is now zero. Now, you won't actually get there because your gases will liquefy at some point and turn into a liquid. But if you were to extrapolate this plot all the way down as you keep decreasing the temperature, measure the volume, well, you reach some constant point. And so that temperature is negative 273.15 Celsius. So at this temperature, it must be the lowest possible temperature that is attainable. And that's absolute zero, we call it. The gas molecules are no longer moving. They're just all hanging out in such a small little volume, and there's no way you can cool it further because you've already taken all the energy out of the system. So you can't cool it down anymore because there's no more heat to take out of it to cool it down. And so we set a temperature scale based off of this. So the Kelvin scale, named after another scientist, has the same spaces between the increments of a degree as the Celsius scale. It just has its 0 points set differently. So the Celsius scale, the 0 point is set to the freezing point of water. The Kelvin scale, the 0 point is set to absolute zero. So they're the same scales, they're just offset by where their zero is placed. We tend to use Kelvin a lot in science because you don't have a sign change on your temperature when you go below or above zero. Zero is only significant in the Celsius scale because that's where water freezes. But if you're dealing with some other substance, going below or above the freezing point of water, which you're not even dealing with, doesn't make any sense. So we use Kelvin a lot for this reason. It's an absolute scale. Your temperatures are always going to be positive, so it doesn't screw up your math by having negative signs suddenly appear, things like that. So definitely know how to use this conversion between Kelvin and Celsius, because we wind up doing this a lot. I'll give you this conversion on the test, but just get really good at using it because we do it all the time. Okay, next up on our list, Avogadro's hypothesis. And so this is the one that says if you have more gas molecules, well, then you have a larger volume, assuming your pressure and your temperature of your gas are held constant. And so the little picture over here is trying to show that if you were to, say, dump some baking soda into some vinegar, it's going to make a lot of carbon dioxide gas. So the more molecules of gas that you make are going to lead to a larger volume for your sample here, because volume and number of moles are proportional. And so Avogadro hypothesized this, and then this experiment was the basis of figuring out the number of particles in a mole, and so that's why the number of particles in a mole is called Avogadro's number. Okay, so now we're back to the ideal gas law. So you can combine all of these individual laws which were discovered first into the ideal gas law equation, which we already talked about. So the ideal gas law is an equation of state in that it describes a current state of a system. It's not talking about a change per se. It's saying, here is your sample of gas, given some pressure and some volume. That's equal to some number of moles, a constant, and the temperature. So this constant, I gave it to you earlier in liters, atmospheres, mole, Kelvin. You can use it in a bunch of different unit systems. You can convert the constant from one unit system to another, no problem. Ultimately, just make sure the units on your gas constant line up with the units that you use in the ideal gas law, and you're set. So how do we use this ideal gas law? Here's a simple example. What's the volume in liters occupied by some mass of nitrogen gas at a given pressure and a given temperature? Well, you'll need the molar mass of nitrogen gas. And remember, since it's diatomic nitrogen, you need to take 2 times the molar mass of nitrogen. So we're going to use the ideal gas law for this. And now, well, we need to think of what parts are going into the ideal gas law here. So we have the pressure, 1.5 atmospheres. We're trying to solve for the volume in liters. For the number of moles of gas, well, we're given a mass of the gas, and we can convert that to moles and then plug it into this equation. And then the gas law constant is given right here. And then the temperature, well, we have 25 Celsius, and we'll need to convert that to Kelvin first before we can use it in this equation. And then once we do, we just plug it right in. Perfect. And 3 sig figs on the number of moles. And here's how we convert Celsius to Kelvin using the equation that we just gave you. And now we plug all of these numbers into the ideal gas equation. Often it's easier to rearrange the equation first before you plug all the numbers in, but ultimately it doesn't matter as long as you solve for the right term. And so we're going to divide both sides by pressure to get this equation. And then now we go plugging things in. So here's the number of moles. Here's the ideal gas constant with its units. Here's the temperature. And then here's the pressure. Now, please, 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 write the units in when you do this math, and then double check that your units actually cancel. This way you can catch if there's errors in your equation. You want to know that before you put the final answer down. So here the moles cancel, the atmospheres cancel, the Kelvin cancels, and we're just left with liters. Perfect, because we want liters, so that's great. So you do the math, you get 2.72 liters, and now you've solved this problem. And when you plug this into your calculator, you get 2.7 liters. Now the sig figs here are limited by the atmospheres. There's only 2 sig figs and 1.5 atm, and that's given to you in the problem, so that limits your sig figs overall. 2.7 liters, there we go. So you can repeat this process and solve for whatever variables you want, depending on what's given to you in the problem. So here's another example. Feel free to forward through the example if you totally get the concept. And what we're going to do here is we're going to solve for the temperature in degrees C of a sample of ideal gas. So you're going to use the ideal gas equation. And then pressure, well, you're given pressure in torr, and the gas law constant we have is in atmosphere, so you got to convert torr to atmosphere, or use the form of the gas law constant that has torr in it already, 62 something something liters torr mole Kelvin. Here we'll do the conversion though, because that's what I have on the screen. Then the volume's 2 liters, that's given in the problem. Convenient, so we don't have to convert grams to moles of something. The gas law constant is here, and then we're trying to solve for temperature. So first, let's convert the torr to atmospheres. So we have 749 torr given in the problem for our pressure. And then there's 760 torrs in an atmosphere. That's given on an info sheet. And this is actually an exact 760, so it doesn't limit your sig figs. And then that leaves you with 3 sig figs out the other side, 0.9855 atmospheres. Now we're to a point where we can just plug things in. So you rearrange the equation to solve for temperature, and then let's start plugging things in. Here's the pressure, here's the volume in liters, here's the number of moles, and here's the gas law constant. So do double check to make sure your units cancel. The atmospheres cancel, liters cancel, moles cancel. You're left with Kelvin on the denominator in the denominator. If you divide by something twice, it pops up to the numerator, so we're going to get an answer out in Kelvin. And our calculator says that's 303.3 Kelvin, with 3 significant figures due to all 3 of the numbers provided in the problem. But we haven't answered the question yet. The question asks for the temperature in degrees Celsius. We have it in Kelvin. So if you subtract 273.15, you're left with 30 degrees Celsius. Now remember, when you're adding and subtracting, your sig figs depend on the decimal place. And so we're significant to the decimal place in Kelvin. So that means we're only significant up to the decimal place in Celsius. So it seems like you lose a sig fig whenever you go from Kelvin to Celsius. And that's just the way it goes. It seems like you gain a sig fig when you go the other way. So the temperature here is 30 Celsius with 2 sig figs. Now you may have noticed that I was a little casual with my conversions from Kelvin to Celsius and vice versa. And that's because that formula there, you can plug numbers in and get an answer out. But if you try to think of the units, it's really just a mess. So ultimately, if you have Kelvin and you subtract 273.15, you'll get Celsius. If you have Celsius and you add 273.15, you'll get Kelvin. Just remember that Kelvin numbers are always bigger than Celsius numbers. And if you think of that when you use 273.15, you can figure out whether to add or subtract. Now, one last thing for this video is to talk about the volume of 1 mole of gas. And for some odd reason, high school chemistry teachers like to make a big deal about this. They say, oh, the molar volume of a gas, 22.4 liters at standard temperature and pressure, where standard temperature and pressure is defined as 1 atmosphere and 0 degrees Celsius. This never made any sense to me. You can use the ideal gas law to calculate the volume of a gas at any temperature. Why are we picking 0 Celsius, freezing? What the heck? So I don't really care about this, but if this is your thing, just go with it, right? And this picture kind of shows you how big a mole of gas is at 0 degrees C. Great. And with that, I'm going to stop the video, and we'll continue on with talking about how to compare changes between ideal gases in the next video. Thanks for watching.